Hi, this is the first lecture for Chapter 5 where we explore gases and their behavior. So Chapter 5 is a nice pivot point for us in this class where we're going to start looking at individual fields of study within chemistry, or individual subjects within chemistry. So we have gases in Chapter 5, Chapter 6 is going to be thermochemistry, and Chapter 7 is electromagnetic radiation. So you get this nice glimpse into these kind of sub-disciplines within chemistry. So it's a nice change of pace a little bit where hopefully you get to feel a little bit of a breath of fresh air. So in order to understand gases, we need to understand their behavior. And the kinetic molecular theory is a theory that describes gas behavior as we observe in our everyday life. So remember, we've talked about the difference between a law and theory in Chapter 1, and you can review that in your textbook if you need a little brushing up. But remember, a law is going to be describing observed phenomena. So if this happens, that happens would be an example of a law, and we're going to look at 4 different gas laws in this lecture. A theory is going to go a little bit beyond that law and try to explain why. So theories are models that we use to understand that phenomena that we observe. The kinetic molecular theory has 5 postulates that explain the behavior of gases that we've observed. The first states that gases are always in motion and subject to the laws of motion. And I like to use this billiards picture here as an illustration of that. So we are familiar with playing pool, or at least the concept of playing pool. And we know that you hit the cue ball, this white ball here, it's going to ricochet off of another ball, sending that ball into motion. So gases, or any molecule, are physical things, and because of that they are subject to the law of motion. We don't often think of them as being physical things, but that's something that we're working towards constantly in this class, is having a deeper understanding of molecules as physical things. So the second postulate is that gases are mostly empty space, and what that's getting at is that a gas is going to uniformly fill its chamber. So if you had a volume of gas, it is going to mostly be empty space, and those gas particles are just going to be moving around inside it. The vast majority of that volume would be empty space. The third postulate is that pressure is due to collisions of gas particles with the container. So a nice example of that, a very straightforward example, would be when you blow up a balloon, you are adding, carbon dioxide into that balloon, and that balloon is expanding because those gas particles that you are putting into the balloon are acting against that chamber, causing the balloon to blow up. Another really good illustration of that comes from your textbook. So here, we have 2 conditions. And, all right, so here we are applying heat. Oh, that's a terrible color. Let's go black, yeah. And we have let's do red. Yeah. Okay, so we have heat. Here we have an open container. We had water in our container that has been converted to gas, so water vapor. Notice that although I've drawn a lot of dots, it is mostly empty space, agreeing with the second postulate of the KMT, or kinetic molecular theory. So that water has been converted, phase change, from liquid to gas. Some of that gas has escaped our chamber in the form of steam. So this is our first condition. Now in this condition, you can see something has changed and the can has collapsed. So one thing that changed is that we closed our container, which is called a closed system. Right, so we don't have gas particles that can enter or exit, and we've removed the heat. So because of that, those gas particles are going to condense to form water again. That water is going to have a much lower volume that it can occupy than those gas particles. Why? Because gas particles are going to uniformly fill their chamber. They're going to be ricocheting off the chamber, and that is what is contributing to our pressure. So when those gas particles condense to form water, there is not enough pressure in the containers. This would be our pressure within the container pushing out, as there is pressure atmosphere pushing in. So our can crumples because we don't have enough gas particles to withstand that pressure atmosphere. So it's a really cool illustration of our third postulate, pressure being due to collisions of gas particles with the container. And right now, I'm recording this lecture from Saco, Maine, which is right by the ocean. So pressure is going to be close to 1 atmosphere. That's the pressure at sea level. And what that means is that we have a ton of gas particles that are bouncing around a very large volume, being our planet and our atmosphere. And that is going to be contributing to everything that you see around you. So all trees, all life, all matter is resisting or pressing against that pressure of our gas particles, or they're pushing against us and we are withstanding it. It's pretty cool. Okay, the fourth postulate is that gas particles do not interact with each other. So KMT is describing ideal gases, and we'll talk a little bit at the very end of this chapter just about what's the difference between a real and an ideal gas, but every gas that we look at in this class is going to be an ideal gas. And ideal gases do not interact with each other. What that means is that they do not attract or repel each other. So you can think of them as being essentially inert to each other. Then our fifth postulate is that the kinetic energy of the particles is proportional to temperature. So kinetic energy with the energy in motion. Here you can see our gas particles are always in motion, right? And if you were to cool down those gas particles, which is being shown in this beaker, then they are going to have very little kinetic energy. Here, if you heated it up, you can see these contrails, if you will, behind those molecules, indicating that they have greater kinetic energy, right, which would be proportionate to their temperature. So here we have our molecules chilled in liquid nitrogen. Over here it would just be your beach ball on a nice sunny day in Maine when we get nice warm sunny days. They happen. They've been happening. Okay, so this chapter is interested in gases, and as you can probably tell from the KMT, we're going to be talking about pressure a lot in this lecture and in this chapter. So our pressure at its heart is going to be equal to force over area. So that force is the product of those collisions of our gas molecules with their chamber. That area would be the size of the chamber. So in the International SI system of units, force is measured in newtons and area is meters squared, and that we call a Pascal, which is just abbreviated PA, Pascal. So we have 4 different units that we can use to describe pressure. One of them I've already talked about, which is 1 atmosphere. So that is going to be essentially the pressure at sea level. The next one is millimeters of mercury. Now we use millimeters of mercury because of this device, which is on the right side of our slide, which is called a barometer. And so the way barometers work is you have this you'd have a glass vial, and you'd fill it with mercury, invert that into a dish of mercury, and what you're going to get is this vacuum at the top of your vial, and that vacuum is going to allow us to know what our pressure atmosphere is. because our pressure atmosphere is pushing down on our mercury that's in our chamber, and if the pressure is high enough, it's going to cause this mercury column to rise. So from the movement of our mercury column, we can determine what our pressure of the atmosphere is. So we use mercury, and millimeter is a standard unit of distance in the SI system, so millimeters of mercury is why we have that name. Now, the inventor of the barometer is Torricelli, and so another unit is a torricelli, or a torr, and that is equal to millimeters mercury. So notice 760 millimeters of mercury equals 760 torr. That means that it's a 1-to-1 ratio. So these 4 units can be used throughout this chapter. You need to be comfortable converting from one to the other. So if you had to go from pascals to atmospheres, you would know that there's 1 atmosphere for every 101.325 Pascal. Now notice that's a pretty huge difference in magnitude. So often with pascals, because that's representing a much, much smaller pressure than atmosphere, we will use kilopascals. Right, and that's just using our metric system to our advantage. Another device that we use to measure pressure is called a manometer. So manometers are really cool. And they're always going to have this kind of layout. So you have one end of your manometer that is open to the atmosphere, and you have one end that is closed, and this is what we call the chamber, or you'll also hear it called the cabinet. And so in that chamber or cabinet, there's going to be a gas, and what we're going to do is use the pressure atmosphere, which we can measure with a barometer, and our pressure of gas, we're going to use the pressure atmosphere, which we can measure from a barometer, and the movement of this column of mercury to determine what our pressure of that gas is. Okay, so let's just do an example of that. All right, so the math here is really simple. It's more about being able to interpret a word problem or a figure. So if you have a barometer, right, perfect barometer, and let's just make our mercury red so we can see it really easily. Okay, so this is our manometer. Mercury's there, and so what we would measure is our difference in height, which we call H, right? So what is that difference in height? Let's say that it's 24 millimeters of mercury. Okay, so we look at a barometer and we see that, shoot, we're at sea level, so it's 760 millimeters of mercury. So now we want to answer the question of what is the pressure of our gas. And we can do that just by looking at our manometer and using a super simple formula. So all manometer problems are going to boil down to looking at the pressure of your gas being equal to your pressure atmosphere, and it's either going to be plus that difference in height or minus that difference in height. Okay, so in this example, if you were to compare these 2 heights on our mercury column, I like to think of it as a teeter-totter. So this would be our pressure of our gas, and this would be the pressure atmosphere. And if you think about this as a teeter-totter, we would know from our childhood that our pressure atmosphere would be heavier than our pressure of our gas. That's also shown by our column of mercury. right? Our column of mercury has what is called a static equilibrium, which means you have these two forces, atmosphere and your gas, and they're pushing down on this column of mercury, and they're going to vie for where that mercury column ends up, and eventually it's going to reach this equilibrium that's not in movement, it's static. So that static equilibrium, we find out, is going to be 24 millimeters of mercury. I know that my pressure of my gas is less than my pressure atmosphere because my column of mercury is higher on the side open to the gas. And so that means that I need to take this formula and take my pressure atmosphere and subtract that height. Why? Because my pressure of my gas is less than my pressure atmosphere. So in this case, my pressure gas would be equal to that 760 millimeters of mercury minus my 24 millimeters of mercury, which would give me 736. Perfect. If instead we had a manometer that looked like this, it's actually better, which is sad, than my last drawing. And let's just, for simplicity's sake, say that that height is still 24 millimeters of mercury. And our pressure atmosphere is still 760 millimeters of mercury. Now I have a reverse teeter-totter from my last one, where this is my pressure of my gas, this is my pressure atmosphere. I know that my pressure gas is greater than my pressure atmosphere. And so I can go ahead and know that my pressure gas is going to be equal to that 760 plus 24. So in this case, it would be 784 millimeters of mercury. There's a first section of your recitation packet is looking at manometer problems. So get some practice. I find a lot of times students find the teeter-totter analogy useful. If it doesn't, forget it. Throw it in the trash. I don't care. Okay, so those are two systems or two instruments that we use to measure pressure. Now we're ready to move on to develop a bigger understanding of gases and pressure and all of these variables that we use to describe gases. So before getting into those individual variables, let's just make sure that we know what they are. So the first one we've already talked about, which is pressure, which we abbreviate with a capital P. The next variable we're going to be interested in is volume, V. We're going to have the number of moles, which is N. And then we have our temperature, which we abbreviate with T. Now pressure, our unit, is going to be any of the units that we've already talked about. We'll see some cases where that unit is defined, but that won't be until towards the end of the lecture. Volume, the liter, is going to be some, the unit is going to be some measurement of volume, like liter or milliliter, blah, blah, blah. Moles, there's only one thing that's moles, and that is the number of molecules, right? That's what a mole is. It's telling us the number of molecules. And then our temperature is going to be in Kelvin. For all gas laws, Kelvin is what you're working with. So remember that Kelvin is going to be equal to your degrees Celsius plus 273. We'll talk a little bit more about Kelvin when we get to a law that deals with it. But our first law that we're going to look at is Boyles Law, which is defined by this equation, which is PV equals K. All right, again, this is called Boyles Law. And what Boyle's Law is describing is the inverse relationship between pressure and volume. Okay, so remember that we have our pressure, we have volume, we have our number of moles, and we have our temperature. So in Boyle's Law, we are looking at situations where these are the variables that are changing. And these are going to be held constant. And so what Boyle's Law is saying is that there's this inverse relationship between pressure and volume. So that means that as pressure goes up, our volume would go down, or if our pressure goes down, that means that our volume would go up. So I really like this figure from your textbook that explains this situation pretty well. So here we have the same number of molecules in each of these systems. These contrails behind them, those three trails, are trying to show that they are at the same temperature, right? And temperature is going to dictate the kinetic energy or movement of those molecules. So they are at the same temperature. There's the same number of them. If we were to measure the pressure and we found that this system went from a lower pressure to a higher pressure, but the number of molecules didn't change and the temperature didn't change, the only way to describe or to explain that would be that our volume of the container shrank. So it became smaller, and that's what this is showing, is that piston, we've added another weight, and it has shrunk that container, pressure has increased. Okay, so number of moles stays the same, temperature stays the same, then we have Boyle's Law. So Boyle's Law says PV equals K, and you're probably like, what the heck is K? K is what is called a proportionality constant. And a proportionality constant is going to be defining that relationship between pressure and volume for a particular gas. So it is specific to the gas that you are examining. So if you knew what the proportionality constant is for nitrogen and you knew what pressure it was at, you could, using those two variables, figure out what volume it would occupy, which you can imagine is pretty useful. What's even more useful about this is that if you have a sample of gas, and let's say it's like this, where you have a volume, let's for simplicity's sake, just say that this is 1 liter, and it is at 1 atmosphere, and now the volume shrinks to 500 milliliters, we could figure out what the new pressure is. And so the way that we can figure that out is because we knew the pressure and the volume of our sample of gas. That sample hasn't changed. We know that there's this proportionality constant, and now we know that the volume has changed, but nothing else has. So the question is, what happened to the pressure? So we can use our proportionality constant as a bridge to compare system 1 to system 2. And so what this really boils down to is what I like to call the working equation of these laws, and that's going to be P1 V1 equals P2 V2. Okay, so let's just do that example really quick that we just had, and we'll do a couple more too, just for funsies. So we have P1 V1 equals P2 V2. All right, so from that last slide, I said our pressure was 1 atmosphere and our volume was 1 liter. Right, so this was, let's just call it system 1. Now we learned that our volume was shrunk to 500 milliliters. And the question is, what is our new pressure? So we're solving for P2. So the way that we're going to do that is isolate P2 to one side of our equal sign, just using basic arithmetic. So we're going to divide both sides by V2. V2 goes away, you get P1 V1 over V2 being equal to P2. So I have 1 atmosphere times 1 liter divided by 500 milliliters. And you should be like, wait, Sam, that doesn't make any sense, right? Because my liters and my milliliters are not going to cancel out. I want to find what my new pressure is. I need my liters to cancel out, so I'm left with a unit of pressure. So instead of saying 500 milliliters, I need to make sure that my units are in agreement so that they go away. So it'd be 0.5 liters, right? 1 divided by 0.5 is 2. And so once you get an answer with these laws, it's really nice because then you can say, well, does that make sense? So my volume went down from 1 liter to half a liter, and my pressure went up. Does that agree with Boyles Law that there's an inverse relationship between pressure and volume? You bet it does. So I haven't violated any of the laws of the universe, which is good. Great part about this chapter is that everything's pretty straightforward and you can get an answer and then ask yourself, like I just did, does that make sense? Okay, so one very cool application of Boyle's Law is in the way that we breathe. So when you breathe, there is some unconscious things that are happening that are controlled by your nervous system. And so we don't often consciously think about our breath unless we're short of breath, right? But it is this incredible display of Boyle's Law in action. So what happens when you breathe in? Breathing in is an active part of your respiratory cycle, being inhale and exhale. When you inhale, what's happening is, that'll show up. Let's make it disinfect. You have your diaphragm, which is this kind of purple blob here. It is going to be pulled down. So it's a muscle. It pulls down. Then here you would have your rib cage, right, over your lungs. And between each rib, you have these intercostal muscles. So those muscles are also going to contract. So diaphragm contracts, those muscles contract, and that is going to open up your thoracic cavity where your heart and lungs live. So what effectively has happened? We have increased our volume, right? So our volume went up. That means that our pressure inside our lungs goes down, right? Volume goes up, pressure goes down. So our bodies, or the system that we're in, which would be the room that we're in, and ourselves, are going to seek a new equilibrium. And so what happens is our pressure of our lungs is less than our pressure atmosphere. And there's this phenomena in concentration gradients where you always have something going from an area of high concentration, and I'm just going to use brackets here because we know that from chapter 4 as being a way of talking about or showing that we're talking about concentration. It always goes from high concentration to low concentration, right? This is passive transport. So our pressure atmosphere is higher than our pressure of our lungs. So that means that air from the atmosphere goes in to our lungs, changing that pressure. We've added molecules by breathing in. Then we have our next phase of the respiratory cycle. So just went over inhale. Now we have when we exhale. And so what's happening there is that's the passive part of our respiratory cycle, where the rib cage, those intercostal muscles that contracted are going to relax. The diaphragm also relaxes. This is part of our elasticity, which I won't get into. Very cool though. So those muscles relax. The relaxation is going to lower our volume in our lungs. So this is when we exhale, so breathing out, our volume goes down, right? We're no longer holding that thoracic cavity open, which means that our pressure goes up, which means that the pressure of our lungs is greater than the pressure atmosphere. So it's going to travel down its concentration gradient, and you have air, in this case containing our carbon dioxide, exiting our lungs. Right? And without that, we wouldn't exist. So Boyle's Law is pretty dang cool. The same analyses can be done for the human heart. That's just a little bit more complicated, but very cool. All right, so let's do one more quick example of Boyle's Law. And I'm just going to go ahead and pull this over to our other program here. Beautiful. All right, word problems galore, right? Because we're in a chemistry class and we love it. All right, so we have sulfur dioxide as the gas that plays a central role in the formation of acid rain. Bummer. True. It's found in the exhaust of automobile and power plants. So we have a 1.53 liter sample of gaseous sulfur dioxide. It's at this pressure. If the pressures change, what is the new volume, right? Temperature and the number of gas particles are staying the same. So because only pressure and our volume are changing, I know I can use Boyle's Law. And remember, I'm going to use that P1 V1 equals P2 V2. So I have 1.53 liters, 5.16. Then we have this change, and this is my new pressure, and the question is, what's my new volume? All right, so P1 was 5.6. V1 was 1.53. Right now we've changed something, and our new P1 is 1.5 times 10 to the 4th PA. V2 is what I'm looking for. So if I want to solve for V2, I would divide, I would divide by P2 to isolate V2 to one side of my equal sign. So I have my new equation, P1 V1 over P2 equals V2. So that's 5.6 times 10 to the 3rd pascals. Times 1.53 liters divided by my 1.5 times 10 to the 4th pascals. Plug that into your handy dandy calculator, which you should have next to you. And I got 0.57 liters. So that is Boyle's Law in action. Remember, number of moles doesn't change, temperature doesn't change. If there's a change in pressure, it can only be due to the fact that volume changed. In this case, our pressure went up, our volume went down. Makes sense. We love it. Okay, so Boyle's Law related pressure and volume. Now we have Charles's Law, which is going to relate our volume and our temperature. So Here we have a different relationship to what we had defined before, and I'm again just going to bring it over to our other program so we don't have to worry about losing our work. Whoops. Okay. So here we have volume being equal to BT. B, again, is a proportionality constant. And again, we're going to use that to create a bridge to compare systems. Again, the name of this law is Charles's law. And unlike our last law, Boyles Law, where we had an inverse relationship, here we're going to have a direct relationship. So we can say that volume and temperature are directly proportionate. What does that mean? That if volume goes up, our temperature must have gone up. Or if volume goes down, our temperature went down. Just like with Boyle's law, this is only true because we have other variables being held constant. So this is when you have a constant pressure and your number of moles. So again, let's go back to that, to the images from our textbook. So here we have the same number of molecules again. Our pressure has stayed the same. They're trying to show that with these two weights. So our gases are able to push against that chamber. Now we can see that we have greater kinetic energy. So these contrails are much shorter than these. So these gas particles are traveling at a higher speed. They have greater kinetic energy. That is going to cause them to bounce off the container that they're in with greater frequency. You would expect that to raise the pressure. The pressure, however, remains the same because we have this adjustable volume container where our piston just went up. We have an increased volume to maintain that same pressure. So our working equation, if you will, needs to isolate our proportionality constant to one side of our equal sign. So that would be V over T equals B. Again, we'll use B as a bridge. And this is going to be our working equation. Now, one critical thing to remember is that our temperature must be in Kelvin. Why? Because Kelvin is the temperature scale that is directly related to kinetic energy. So it's an absolute scale. So absolute zero would be 0 Kelvin. That just looks like okay. So let's do that. 0 Kelvin. And at 0 Kelvin, there would be zero motion in our particles, which doesn't actually happen. So absolute zero can only be approached. It cannot be reached. Part of that also has to do with the nature of temperature. Temperature is transferred from one object to another. You can't have something that is colder than absolute zero, so you can't get below it. This is super important. If you use Celsius, you will get the wrong answer. So in this chapter, remember to convert to Kelvin. All right, so another cool example of that would be with a balloon and liquid nitrogen. So here we're really cooling off those molecules. That's going to reduce their kinetic energy. So temperature goes down, kinetic energy goes down. Because of that, our volume shrinks, right? Because the pressure atmosphere hasn't changed. Very cool. All right, so let's do an example of that. so we have a balloon filled with this volume and that temperature, then it's cooled. Okay, so we have a system under one set of conditions. Now one of those conditions has changed, and the question is, what's the final volume? Right, so let's work through it. So we have 700 milliliters, we have 200 degrees Celsius, 100 K. All right, so our volume initially is going to be 700 milliliters. Our temperature is 20 degrees Celsius. And so when you see something that says 20 degrees Celsius, a lot of times I would box that and draw an arrow to remind myself that I need to change that to Kelvin, right? So Kelvin is 273 plus our degrees Celsius. So we have 293 K. So that is our first set of conditions. Now we've changed it so our temperature 2 is 100 K. And the question is, what's the new volume? So we have our working equation of V1 over T1 equals V2 over T2. We're solving for V2, so we're going to multiply both sides by T2, isolating volume to one side of the equal sign. So we would have 100 K times our V1, which is 293, oops, that's not V1, 700 milliliters, yeah, divided by our T1, which is 293 K. Right, so you plug that into your calculator and you should get 239 milliliters. Does that make sense? Well, our temperature went up. Nope, our temperature went down. If our temperature went down, we would expect our volume to go down. Is that what we had to happen? Yeah, it went from 700 to 239. It's really important to use those subscripts. Keep yourself straight when you're looking at one system versus the other. All right, the next law that is, again, holding something's constant, allowing other things to change, is Avogadro's law. Avogadro's law, you can imagine, is going to be dealing with moles. Because you're smart, wicked smart. Okay, so this is our volume being equal to AN. A is our proportionality constant. Again, we have this direct relationship. Which means that volume would go up when moles go up, or our volume would go down if our number of moles went down. This is only true because pressure and our temperature are constant. So let's just look at our example, our figure from our textbook. So here we have our cylinder. Pressure is the same, or the same weight that's pushing against, that our molecules are pushing against. So temperature stays the same. Notice that we have the same length trails behind them, showing the same kinetic energy. If our volume increased, the only explanation would be that we injected gas into our system. This would require, as we have more molecules in our chamber, there's more collisions with that chamber, you would expect the pressure to go up, but it does not, because we can adjust that volume, and in fact it adjusts to get larger, as we would predict. So again, we're going to rearrange our equation so that A is on one side. We use A as a bridge to make a comparison. So our working equation, if you will, is going to be V1 over N1 equals V2 over N2. All right, so let's do an example. So suppose we have, and I'm actually just going to bring all of this over because we're going to need to work on this one for a second. Perfect. Okay, suppose we have a 15-liter sample containing 1.5 moles of oxygen and excess hydrogen at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. If all the oxygen were converted to water vapor at the same temperature and pressure, what would be the volume of the water vapor? Okay, so this is an Avogadro problem. We know that our working equation for Avogadro problems is going to be V1 over N1 equals V2 over N2. We have an original volume of 15 liters. It contains 1.50 moles of oxygen. We're told what the pressure is, we're told what the temperature is, but then we're told that it's staying the same. So all we care about is our volume and our number of moles. Everything else is held constant. Those are the conditions that allow us to use Avogadro's law. So if all of the O2 is converted to water vapor, what would be the volume of the water vapor? So you have your initial volume, then you have your initial number of moles, 1.5. And now we have this change, so system 1 to system 2. So we need our number of moles, and our volume is our question. So we're not told what our number of moles is for our water, but we are told that all of the oxygen is converted to water vapor. Given information about a reactant, asked about information for a product, sounds like we have to do a little stoichiometry. Super simple stoichiometry. We're ready for this. So we're going from oxygen to water. So we have 1.5 moles of O2. From that 1 mole of O2, we get 2 moles of H2O. So we have 3 moles of H2O. And now we can make our comparison. So we are solving for V2. Let's multiply by N2 on each side. So we have N2 V1 over N1 equals V2. Whew. Subscripts, important. Staying organized, super important. So here we'd have 3 moles times our volume 1 of 15 liters. Divided by our 1.5 moles. Multiply that together and you should get 30 liters of water. So we can't forget everything that we've learned in chapter 3 and 4. When you get stuck on a problem, ask yourself if you have the tools to find the information that you need to solve. Okay, so thus far we've explored Boyles, Charles, and Avogadro. All of those we're looking at 2 variables, everything else remaining the same. Now we get to graduate to the ideal gas law, which puts all of those pieces together into a new equation that allows us to change multiple variables. So here we have PV equals nRT. Pressure is going to be an atmosphere. So when you use the ideal gas law, you have to obey the units of our constant. So now we have a constant that is true of all gases, unlike the proportionality constants that we were looking at before, and that is R. And R is called the ideal gas law constant. Very well named. So creative. So because our constants unit is liters times atmosphere over Kelvin times mole, we need to make sure that our pressure is in atmosphere, our volume is in liter, and our temperature is in Kelvin, moles is in moles. Right? We have to obey the units of our constant so that we can cancel them out and come to the problem that we want to solve. Okay, so that's funny. Here we go. So here we have a random sample of gas. And let's say I wanted to know what the number of moles were. So I'm curious, okay, how many moles do I have? Let's say that this is at a temperature of 25 degrees Celsius. It's at a volume. The volume of my chamber is, let's call that 20 liters. My pressure is going to be 200,000 pascals, and N is what I'm solving for. So I would have to use PV equals nRT to solve for N. So I want to isolate N to one side of my variable, or one side of my equal sign, excuse me. So it'd be PV over RT equals N. I'm using R, which means that everything has to be in the right unit. So I need to change degrees Celsius to Kelvin. You always have to do that in every single problem in this chapter. It's 298 K. Volume is in liters, that's great. But here I have 200,000 pascals. So I need to use the relationship between Pascal and atmosphere, because that's what our unit is in. So I know, I can use my quick little picket fence here, there's 101.325 pascals in 1 atmosphere. So you get 1.97 atmosphere. Okay, so now everything's in the unit that I need. So I can say my pressure is 1.97 atmosphere times my volume of 20 liters divided by 0.08206 liters atmosphere over Kelvin mole times my temperature of 298 K, and that is going to give me my number of moles. Now it's really good here to just ask ourselves, do my units cancel out? Did I set this up correctly? So my Kelvin would cancel out here, my liters cancels out, my atmospheres cancels out. That would give me 1 over mole in the denominator. Dang. 1 over mole in the denominator, which would give you it in the numerator. And let's see if I can remember what those numbers were. So it's PV over RT equals N. It was 1.97 atmosphere times our volume, which was 20 liters, over 0.08206 liters atmosphere per Kelvin mole, times 298 K. Whew, pulled it off. Okay, so 1.97 times 20 divided by 0.08206 times 298. That's in parentheses so that the order of operations is followed. That means that I have 1.61 moles of my mystery gas, because I never told you what I did. I could then figure out how many grams I have. I could do stoichiometry with that. Lots of places to go. So that is one application of our ideal gas law constant, but what we're gonna see is that a lot of times we're gonna use our ideal gas law constant in the same way that we've used our other gas laws. by comparing a system that has changed. So again, when we were looking at Charles and Boyle and Avogadro, everything else was held constant and we just had 2 units changing, or 2 variables changing. Now, multiple things can change. So if you have both pressure and volume changing, if you have number of moles and pressure changing, the only thing that you can use, the only tool at our disposal, is the ideal gas law. So let's get that back on the board here. So it's PV equals nRT. And what you want to do when you're comparing 2 systems is you're going to get the variables that change to one side of the equal sign and the things that stay the same to the other side of the equal sign. In doing so, you're essentially creating that bridge that we used in all of the other laws, right? They were the proportionality constants. In this case, it's going to be those variables that don't change. And then we can figure out what the consequence of that change is. Okay, so we have a sample of diborane gas. It's a substance that bursts into flame when exposed to air. That's pretty cool. It has a pressure of blah, 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 and a temperature of blah, 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 and a volume of blah, blah, blah. If conditions are changed, so that the temperature and the pressure change, what would the volume of the sample be? Ooh, interesting. Multiple variables are changing. I cannot use Boyle, Avogadro, or Charles. That means I have to use my ideal gas law. So let's go ahead and just set up our systems. So in system 1, I have the variables underlined in red. So that's 345 torr. I have, so that would be P. My temperature is negative 15 degrees Celsius, and you should immediately just change that to Kelvin, just the minute you see it. So 273 minus 15 is 258. Then we have our volume, 3.48 liters. All right, so now let's make system 2, and I think this would be called periwinkle. It's not quite a periwinkle, it's more like a sky blue. Our new pressure is 468 torr. Our new temperature is 36 degrees Celsius. Let's go ahead and change that to Kelvin. So 273 plus 36 is 309 K. And the question is, what is our new volume? Okay, so that means that my number of moles and my ideal gas law constant R doesn't change. It's a constant, it's never going to change. So these two I need to isolate to one side of my equal sign. So I'll do that by dividing by temperature. So then I have PV over T is equal to NR. I can use that, those things that remain constant, as a bridge to relate my 2 systems. So now I have P1 V1 over T1 equals P2 V2 over T2. I need to isolate for V2, so I'm going to multiply both sides by T2 over P2. Those cancel out. We get our new kind of working equation of P2 V1, T2 P1 V1 over P2 T1 equals V2. Whew, keep your subscripts straight. All right, now we just plug and chug. And notice, Kelvin, I had to convert to. I had to convert my Celsius to Kelvin. I don't care that pressure is in torricelli, right? Because I'm not actually using R right now. It is being used as a bridge, but my two Torricelli units are going to cancel each other out, and I'll end up where I want to go. Right? You can't do that with degrees Celsius. Why? Because that's an additive property, right? You add 273. Or I guess we make that conversion. I shouldn't say it's an additive property. You make that conversion by adding 273 to your degrees Celsius. With pressure, those are all proportionate to each other, right? We're multiplying by a conversion factor. Okay, so this is 2, 2, 2. This is 1, 1, 1. Let's plug it in. So T2, 309K. P1, 345 torr. V1, 348 liters. Divided by P2, 468 torr. Times our T1, 258K. You want to double check after you plug these values in that you didn't confuse V1 for V2 or P1 for P2. Just make sure that you set them up correctly. Okay, so you plug that into your calculator and you should get 3.07 liters. All right, so those are the gas laws, and the second lecture is going to be dealing with some more gas behavior and some gas stoichiometry. So get a lot of practice with this before you move on to the second lecture, and enjoy it.